What's up, everybody? We're back on Mr. Murray's Math Land doing another calculus optimization problem. Another classic that sometimes gives kids fits. It's trying to inscribe a rectangle of maximum area inside a semicircle with a given radius. So in this problem, we are talking about inscribing a rectangle of maximum area, the biggest rectangle we can, inside a semicircle with a radius of 6. Okay, so a couple ways to go about this. First of all, of course, always read your questions carefully and keep in mind one of the basic strategies. Whatever you're trying to maximize or minimize, whatever you're trying to optimize, that is, that's what you need an equation for so that you can do the derivative on it, set it equal to 0, do some calculus on. So I need an equation for the area of this rectangle. So that's what I'm going to work on here. So the area of a rectangle is, of course, base times height, but let's see what we can do with this semicircle. So first, they said the radius is 6. So given that that's 6 there, it might make it a little more natural to, rather than just call this whole side of the rectangle x, it might make it easier to call just this portion x and to call this portion x, since you're kind of cutting into the radius that much of it. And if that's x, let's call the height y, or you could use base and height if you like. So right now I've used x and y, so I could define my area as being this whole base, which is 2x times that height of y. So the area of this rectangle is 2xy, which is great. That's a start, but remember, you now need to find a way to describe it all in terms of one variable. So I need to find a way to substitute in for x or y, and that's in some way using this radius. So keep in mind, the radius can be redrawn anywhere from the center to the circle, to a point on the circle. And so if you redraw it right there, you get the right triangle. And so we can use a little Pythagorean theorem. So x squared plus y squared will always be that 6 squared. X squared plus y squared will always be 6 squared, or 36. And now you can use that relationship to solve for x or y and substitute into your area function. So I'm going to solve for y, so y squared would be 36 minus x squared, and y would be plus or minus the square root, of course, but it's a distance, so it can't be negative, so just going to be the square root of 36 minus x squared. And I'm going to take that and substitute that into my area function over here. So the area will always be 2x times, and I'm going to take out that y, and I'm going to replace with root 36 minus x squared. Another way you could have done this is, if you are sort of more of an algebra 2 type of person, you could have imagined that this was on the coordinate plane, pictured the y-axis going right through the middle of that circle, and pictured a circle centered at 0, 0 with a radius of 6. And maybe you remember your conic sections, that the equation of a circle is always x squared plus y squared equals r squared. And that's where you would get this same relationship of x squared plus y squared equals 36. And that would represent the full circle, right? And when you solve for y and you get plus or minus, the minus is the bottom semicircle. The top is the positive. So, the plus or minus is really two separate functions, because collectively it fails the vertical line test. And so, anyway, I just think that's a cool thing to remember. Your conic sections kind of just come from those basic geometry relationships. So, either way, but now we've got this here to deal with, and we want to find the derivative and then set it equal to 0, right? And this derivative wouldn't be terrible. It's a product rule. There'd be a little chain rule inside that square root, of course. But this would be a great time to refresh on how to use a calculator to help you do this kind of thing. So let's pull up the calculator. I'm going to go to y equals. Let's just say I'm not feeling comfortable with my derivatives, or I'm feeling a little shaky, but I'm really good with my calculator. So, or at least this would be a great way to check. So I'm going to input this function into y1. Okay, 2x 36 minus x squared. And if I want to see the graph of this, I would hit graph. If I want to see the graph of its derivative, which is what your calculator can do, and you have all these options. I just think this is a cool thing to explore. Remember, you can go to y2 and hit math 8. That's the end derivative there that you can see. Scroll down to it, or just hit 8, and that brings back this. And so this, we're taking the derivative with respect to x. That's that first thing. This is what you're taking the derivative of, which is that whole 2x times root 36 minus x squared. Or you can use alpha trace y1. There's a little shortcut name for it. You're taking the derivative of y1, and remember, this part of it is always at what x value do you want the derivative? Well, I want to see the graph. I want to see f prime of x. So I want to see the whole thing, so you actually put x there. So it's for all values of x. And if you like, if you don't want to see the graph of the original area function, you just want to see the derivative, then you can unhighlight that equal sign. And now the only graph will be y2. Notice my stat plots are also off for those of you AP Stats kids, make sure those are unhighlighted at the top. And if you like, before you hit graph, you might want to change your windows. Use a little logic here. Your x values, your x represents that piece of the rectangle there, right? And x has to be something bigger than 0 but less than 6. So you could really just give yourself a nice clear window here by changing your x minimum and maximum to 0 and 6. Y min and max, that might be fine as it is. You might need to change that, but let's just see. Let's hit graph, and let's see that derivative function. And there we go. We see it crossing the x-axis, and notice we finished our graphing unit. We see it crossing from going above to below, so that's the derivative changing from positive to negative values, which indicates a relative maximum on my original. So just keep in mind that anything you use your calculator for is fine as long as you represent it on paper with notation. And so I'm just skipping over all the middle steps, but what would I be doing if I did it by hand? I'd be finding the derivative and finding where it equals 0. So there's the equation I'm solving, and I'm using the calculator to solve it. So a prime is equal to 0 for x equals, and now let's get it here. So how do you calculate the 0? I can see it's between 4 and 5, a little bit more than 4, so second trace 0, and you can hit 4 as your left bound, or scroll if you like. Right bound, you can scroll to the right, or you can actually type 5 as your right bound and hit enter for your guess, and there we go. So the 0 is at 4.2426, and you might like to write a lot of decimal places because this is not the final answer. If you want to write only a few, 2, 4, 3, that's fine. Accurate to 3 places, rounded or truncated. But keep in mind that you are trying to find the dimensions and the area. So this x is really not the final answer. So this is one of these cool tricks with the calculator that's nice to know when you're solving a larger problem and you need to use that x value for more things. Let's pull back that full value and store it. So I'm going to hit second answer. That brings back the last thing we calculated, which was that 0 value, 4.2426, etc. And I'm going to store it, and you can pick any letter you want. I'm going to store it in A. And you'll actually see the AP often do this in their FRQ write-ups, that they'll say for x equals blah, 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 and they might even write in their work, and let that, well, they probably wouldn't pick A because A's already been used in the problem, but they might say it equals C. And then throughout the problem, you could just cite it and use C. But either or, now what am I doing? I want to take that value, and the dimensions of my rectangle were, remember, 2x by y. 2x by y. So 2x is equal to and keep in mind that we should be justifying that it was a relative maximum, because we saw on the graph, I don't have to do any checking, I saw that A prime changed from positive to negative, went from above to below, which tells me that the area was increasing up to that point and then decreasing, so we're good with that. So your dimensions are 2x, but notice if you multiplied your rounded value by 2, you wouldn't get the same thing. You'd be slightly off, so this is why it's beautiful. You can just say, hey, what's 2 times A? And that's going to use the most accurate answer, and that would be 8.485. And so 8.485. Finding your dimensions, and your y value is root 36 minus x squared. So you want to plug your x value in there, and this is, again, great. I can just, on the calculator, say, all right, it's going to be root 36 minus that a value squared, and I don't have to worry about rounding off my decimals. I mean, you could just go beyond 3 and write it out and be careful, but notice what you get. For y, you get about 4.243. Okay, so those are the dimensions, and now find the area. Well, you could do 2x times y, or remember, you have an area function here that you created, which is all based on x after you changed it into all x values. So that's stored in your y1. So another cool little trick, remember, you can do, the maximum area is going to be when x is this value. Just plug it into your area function. But again, I could use the stored value, so I could do alpha trace of y1. So this is like I'm doing a of that x value I stored. Probably a bad idea that I used a, because I keep saying a prime, and then this a to represent x, but you get the idea. You could store it anywhere on your calculator. But notice the area I get, so the area of 4.243, that's when x was the optimal value, gives you 36. And even notice though, even though I wrote this 3 decimal rounded value, I actually on my calculator used the full decimal, so I got the most accurate answer of 36. So here we go. Let's just answer it here. The dimensions are, it was 8.485 by 4.243, and the max area is 36 square units. I don't think there are any units in here, but never a bad idea to think about that. Okay. So this is a, kind of a tricky problem, but hopefully you got the hang of it, and hopefully you brushed up on some of your calculator tricks to help you out too. If not, you can feel free to do it by hand, but just trying to show you some stuff. Got any questions, let me know, or keep working hard, and we'll hang in there and keep hanging in there, right? All right, take it easy.